So we're going to talk about the intermolecular forces. What are these things that hold molecules together? The strength of intermolecular forces is going to depend on the structure of the particles, whether those are atoms or polar molecules or nonpolar, etc. What state a particular type of matter is in at a given temperature, liquid, solid, gas, is going to depend on the strength of the intermolecular forces. If you have strong forces holding those particles together, that substance will have high melting points and boiling points. If you have weak forces, the melting points and boiling points will be low. These intermolecular forces arise from interactions between charges. So these are electrostatic attractions. There may be charges, they may be partial charges as in polar molecules, or they may be temporary charges on particles. So we're going to review Coulombs Law here. This first part, the 1 over pi epsilon naught, is just a constant. What we're interested in is the potential energy is equal to this constant times Q1, Q2 over R. Q1 and Q2 are the charges of the particles. As these charges get larger in magnitude, E becomes more negative. So the potential energy becomes more negative, and that's a greater attraction. As R, the distance between the particles becomes smaller, as the particles get closer together, the attraction increases. Okay, so those are concepts to keep in mind. Bonding is different than intermolecular forces. So bonding involves charges, oftentimes full charges like +2, -1, etc., at very close distance. Here in a water molecule, a bond length is about 96 picometers. So that's a close distance, whereas the intermolecular forces are going to operate on a larger scale. The distance may be more like 300 picometers. So if you increase the distance between the particles, the attraction decreases. So just for that, intermolecular forces are weaker. But they also often deal with smaller charges, partial charges or charges that are temporary. We're going to talk about 4 different types of intermolecular forces. We'll start with the weakest, dispersion forces. Dispersion forces are present in all molecules and atoms. Even the noble gases have dispersion forces. These forces go by different names, sometimes called London force, London dispersion force, van der Waals forces, induced dipole forces, etc. I'm going to try to stick to dispersion force because that's what your book uses, but it might slip up. London force.
Why is London so good?
Well, I think it was a scientist named London. Pretty sure. You could Google that. So what happens is the electron cloud can fluctuate. So here we have an atom of helium. We have 2 electrons. And if you would just take, pictures of it at different times, you could pinpoint where the electrons are, and they might, on most of the time, they'll be kind of scattered about. But every once in a while, both of the electrons might end up on the same side of the atom. This reminds me of a time when I walked into the living room and I saw all 6 of my children sitting on half of the couch. I took a picture because, I don't think that had ever happened before, and it'll probably never happen again. Just spontaneously, all 6 of them on half the couch. Random, right? They were looking at something. But that can happen with electrons too. Most of the time, they're just all over the place, right? But sometimes they'll kind of clump up just randomly. When that happens, we have a charge distribution that's not equal anymore. The electrons, the negative charges, are on one side of the atom, and there's no negative charges over here. So that kind of exposes the nucleus with the protons in it. So you have this dipole within the atom. Partial negative on one side, partial positive on the other. Everybody okay with that? Just getting lopsided. Well, that happens in one atom, and then the neighboring atom, these electrons in the neighboring atom see this positive charge on the next atom, and they're attracted to it. And so they come over here, and that causes an imbalance in the next small atom. It's a little bit like going on a cruise on the San Francisco Bay, and the people are all over the deck, right? You go by Alcatraz, and everybody goes to one side of the boat. They're attracted. Everybody wants to see Alcatraz, right? So the boat maybe lists, hopefully just a little bit. Hopefully they didn't violate the loading limits and stuff. So the spontaneous dipole on this one induces a dipole on the next one. Now we have a partial negative and a partial positive, and there's an attraction between the atoms. This one being lopsided can induce a dipole on the next one, and this can happen all over the place. This dipole then goes away. These are temporary, fraction of a second, and then they're gone. They come and they go, and they come and they go. And so this is what the dispersion force is. It's an instantaneous attraction between these temporary dipoles. Any questions? As you can imagine, this force is very weak because it's not even present. Each individual attraction is not even present all the time. It just comes and goes.
Yeah, you missed.
You missed it. You can watch the video.
Because you were late.
You were late. I saw you be late. It's okay. So the magnitude of the dispersion force, how strong it is, depends on how easily those electrons can get lopsided. So a larger electron cloud is easier to polarize. Polarize means to become different on each end, because the electrons are held less tightly. They're farther out. They are not as attracted to the nucleus, and so they can get lopsided more easily. So we observe that dispersion force generally increases with the molar mass of the substance. So here's a table showing the different noble gases. Their molar mass increases, and the size of the atom increases. The boiling point of a substance gives us a clue about the strength of the intermolecular forces. Noble gases only have dispersion forces. If we have a low boiling point, like helium boils at 4 Kelvin, that's like crazy, crazy low temperature. That means there's very little attracting those atoms together. Because the weaker the forces, the weaker the forces, the lower the boiling point. So you can freeze helium, but it's pretty hard to do.
They've gotten down to that close to.
They've gotten extremely close to zero, like 0.04 or something.
I think that
Kelvin.
our ability to say 0.45 nanokelvins. The record.
Okay, yeah, 0.45 nanokelvins. Something like that is just really low. Remember, absolute zero would be the temperature at which all atomic movement ceases, not even any vibration.
I'm going to be really curious to see if they actually get to what 0 Kelvin is and discover that they've been quite wrong and that's not actually what takes place at that whatever temperature that is.
Yeah, well, a lot of things are like that, and there's obviously a lot of people that are curious about that because they're spending a lot of money trying to get to 0 Kelvin, and is there any, huge benefit in doing that? Is there any fiscal reason to do that? No, it's just simple curiosity, but that's the beauty of science.
Is that where the Einstein-Bose
The-
movement or whatever that is comes into play?
That would be physics, and I only retained the physics that I need to understand chemistry. Yeah, the brain has a limited amount of storage, so you just have to delete things at some point. So we see the boiling point increases as the size of the atom increases, and that tells us that the strength of the intermolecular force, the dispersion force, increases with size. The shape of the molecule can also play a part. So here we have N-pentane and neopentane. And these have exactly the same molar mass because they have the same chemical formula, but the atoms are connected in a different way. So we see that N-pentane has a boiling point of 36. Neopentane boils at 9 degrees Celsius. So this obviously must have weaker dispersion forces than normal pentane. The reason for it is this. N-pentane is more cylindrical in shape. And so we've got these sides that provide more surface area for interaction. I often think of these intermolecular forces as being like Velcro. And so if you think of these as objects covered in Velcro, these are going to stick together much more strongly than two spheres would stick because you can only get this one point of contact. There's very little Velcro holding them together. They're going to fall apart very easily. So the shape of the molecule plays a part as well. Any questions? This is a concept that's important in organic chemistry. Here we see a graph showing the different straight chain alkanes going from 5 to 9 carbons. So the molar mass obviously increases, and the boiling point also increases, and it's really very linear. And that has to do with the molar mass. The electron cloud is more easily polarized, and we have, because it's longer, we're also getting more surface area. These guys have more surface area to stick to each other than these guys do. The next force is called a dipole-dipole force. And this is present in all molecules that are polar. So this is why we're talking about this after we've discussed molecular shape and how do you figure out if something's polar or nonpolar. Dipole-dipole force is stronger than dispersion forces because these are attractions between permanent dipoles. There's always the dipole there. It's not that it's coming and going. So if you look at a space-filling model of acetone, we see there's a permanent dipole here. The oxygen has a partial negative charge. The hydrogen side has a partial positive charge. So there's an attraction between the oxygen on one acetone molecule and the hydrogens on a neighboring acetone molecule. Here's the electrostatic potential map showing the electron density. And we've got this red end attracted to the blue end. Polar molecules also have dispersion forces. So the dipole-dipole force is in addition. We see that polar molecules have higher melting and boiling points than nonpolar molecules of similar size. If we compare formaldehyde and ethane, so their molar masses are almost identical, which tells us that their dispersion force strength is probably similar. We look at the boiling points, minus 19, minus 88. Big difference here. It can't be due to dispersion forces because those should be pretty much similar. And if we look at molecular shape, they're both kind of globular, right? There's not one that's long and skinny. The difference is that this molecule is polar. So we look at that central carbon atom, and we see there's no lone pairs on it, but one of these atoms bonded to it is an oxygen and the other two are hydrogen. So this is not symmetrical because oxygen has a different electronegativity than hydrogen. So this is a polar molecule. This is nonpolar. So do you remember the rules I taught you about how do you figure out if it's polar? It's nonpolar if there's no lone pairs in the central atom and all the atoms bonded to the central atom are the same or have the same electronegativity. So when we look at this, there's not one central atom, but there's two interior atoms. No lone pairs. But how do we deal with this one has 3 hydrogens and then this carbon? Well, a carbon-hydrogen bond is essentially nonpolar. The difference in electronegativity is 0.4. And so this is one addition to Mrs. K's simple rules for determining polarity that you need to remember. So carbon-hydrogen, nonpolar. So if all of these bonds are nonpolar, carbon-carbon's going to be nonpolar, then this molecule can't possibly be polar. Question?
Is there a rule like if it's equal to or less than 0.5, or if it's greater than 0.5 then it's polar? Or if
The
it's 0.4
division
below?
is at 0.4.
0.4?
Yeah.
0.4 or below?
Yeah. So remember, we had that continuum of completely nonpolar to polar to ionic.
Right.
And we've sort of arbitrarily made some dividing lines in between. But alkanes like this with just carbon and hydrogen, we know from experiment are very nonpolar.
Also,
Yes.
are you going to give us the electronegative values for the elements on the tests?
No, I will not give you the electronegativity values. Because I'd rather have you just say, well, carbon, oxygen, that's going to be a polar bond. Because they're different. That works like 95% of the time. And it will work on all the questions I give you. I do, though, want you to know that a carbon-hydrogen bond is a nonpolar bond. So it's the one exception I want you to remember. So higher boiling point, higher melting point due to the dipole-dipole forces. Pardon me? Carbon-hydrogen is a nonpolar bond. That's the only exception I want you to remember. It's the only really important one. Here's boiling point versus dipole moment. Remember what dipole moment was? The dipole moment was the measure of the dipole in a polar molecule. So greater dipole moment means this molecule over here, acetonitrile, is more polar than propane. Propane is essentially a nonpolar molecule. Its dipole moment is almost zero. Here we've got 5 different compounds with very similar molar masses. So the dispersion forces should be very similar. But what we see is increasing polarity gives us increasing boiling point. So the more polar it is, the higher the boiling point. Polarity is very important in determining whether substances will mix with each other. So miscibility is the fancy word, meaning the ability to mix without separating. And it refers to liquids. You've got 2 liquids, you got oil and water. Will they mix without separating? Oil and water will not. They are immiscible. But something like ethanol and water will mix just fine because they're both polar. Our little rule of thumb here in predicting miscibility is like dissolves like. So if you have 2 polar substances, they will probably mix. 2 nonpolar substances, they'll probably mix. If you have a polar and a nonpolar, not so much. Here we have pentane and water, and they are not going to mix. Pentane, C5H12, anything with just carbon and hydrogen is going to be a nonpolar molecule. This is nonpolar, water's polar, they don't mix together. Any questions? So this is an example of the type of question you should be able to answer. Which molecules have dipole-dipole forces? Well, what kind of molecules have dipole-dipole forces? Polar molecules. So we have to look at these and identify, are they polar or not? You really should draw Lewis structure. So Ci4. So carbon with 4 iodines bonded to it. And I'm just going to do these quickly because we've already gone over how to do Lewis structures. So this is the Lewis structure that we come up with. Polar or nonpolar? Nonpolar. These are polar bonds, carbon and iodine, but carbon has no central atoms. Carbon is a central atom. Carbon has no lone pairs, and all of the atoms bonded to it are the same. So this is a nonpolar molecule. Does it have dipole-dipole forces? No. It has to be polar to have dipole-dipole forces. Okay, CH3Cl. So 3 hydrogens and a chlorine. Even without finishing that, polar. Here we've got a central atom, carbon. It's got 3 hydrogens and a chlorine. Chlorine has a different electronegativity than hydrogen. So that's going to be polar. So a polar molecule, we're writing polar. I'll turn that into a yes. Yes?
Do you need to know the direction of which the moment is happening?
In this question, no, you don't.
So you don't know the values of the...
It would depend on the strength of the dipole in each bond.
Right. So if chlorine was more dipole than carbon, then the moment would be happening towards chlorine?
Yeah, so chlorine is more electronegative, and we know that from just the trend on the periodic table. But then if we're talking about, overall direction, we also have to think about the molecular shape.
Okay.
This is tetrahedral, right? And so then you'd have to draw a 3-dimensional thing and show that the dipole moment would be pointing towards chlorine. Mostly, though, what we're interested in is having you learn how to look at a chemical formula and determine, is it polar or nonpolar? Which direction the dipole moment points is really not that important. We want to be able to identify, this is a polar molecule, this is a nonpolar molecule. How about HCl? That would be polar. So this is a diatomic molecule. There's only two atoms. There's only one bond. If the bond is polar, the molecule's polar. Okay? So hydrogen and chlorine are different. They are not the same. And so I would expect you to predict that's polar. It is. And so yes, it has.
And also being a strong acid is an indicator. Correct?
It is a strong acid when it's dissolved in water.
Because, all strong acids dissolve in water, correct?
They do. And all strong acids happen to be polar. But there's not a causal relationship there. There's a correlation. Any questions? Third type of intermolecular force, hydrogen bonding. This is a dipole force on steroids. Super dipole force, right? He's got a cape and everything. So this is found in polar molecules. Thank you. People in their mufflers, good grief.
Sounds like a shape of
Man,
baseball cards and stuff.
I know, right? Baseball cards on the spokes of your bike. So this is found in polar molecules, but only in particular polar molecules. Ones in which you have hydrogen bonded to fluorine, oxygen, or nitrogen. And the significance of these three is that they are small atoms, and they are the most electronegative elements. So we get this dipole force that's extra strong because the amount, or the magnitude of the partial charges is larger because of this difference in electronegativity, and the distance is going to be small because the atoms are small and they can get close to each other. So that's why it's extra big. So how do you remember fluorine, oxygen, or nitrogen bonded to hydrogen? No. E.T. What did E.T. say? Phone home. He'd point at the sky. E.T. phone home, right?
I think ethno is more memorable.
Phone home. So fluorine, oxygen, or nitrogen bonded to hydrogen. Oh, yeah, look at that. Phone home. You can use whatever thing you want, but I like E.T.
Oh.
So here we've got ethanol. In ethanol, there's a hydrogen-oxygen bond. So that fits the phone home part. And it's a polar molecule, and so we see the hydrogen bond is the attraction between the hydrogen in one molecule and the oxygen in another molecule. It's not the bond between hydrogen and oxygen in the same molecule. That's a covalent bond that's completely different. Hydrogen bonds occur between molecules. Here we have water molecules. Oxygen-hydrogen bond in a polar molecule. So we have these hydrogen bonds represented by the dotted lines between the hydrogen on one and the oxygen on another molecule. Any questions? So important to remember, hydrogen bonds are between molecules. Chemical bonds are between atoms within a molecule. Hydrogen bonds are the strongest intermolecular force present in pure substances, but they are only 2 to 5% as strong as a covalent bond. So covalent bonds are way stronger. We see that compounds with hydrogen bonds have higher melting and boiling points. Here we've got ethanol and dimethyl ether. Same chemical formulas, same molar mass, same dispersion forces. They both have dipole forces. But look at the boiling point difference, 78 positive versus minus 22. So this molecule, although it does contain oxygen and hydrogen, doesn't have hydrogen bonded to oxygen. So if we draw the structural formula for that, it's going to look like this. The oxygen here is bonded to carbon, not to hydrogen. So there's no hydrogen bonding. In ethanol, This is why we draw condensed formulas, because it gets real tedious with all the H's. We've got the oxygen-hydrogen bond. So there's hydrogen bonding. Any questions?
Probably doesn't exactly pertain, but how do they make each of those, considering they've got all the same stuff, but they come together differently? And if we're doing a calculation that has, all the stuff to make both of those on the left side, how do we know that it makes one of those?
So that's a really good question. These have the same 2 carbon atoms, 6 hydrogen atoms, 1 oxygen atom. How would you make this one instead of that one? Or if you just have the ingredients, how would you know which one is made? That's your question?
Yes.
You would take organic chemistry.
Okay, so it doesn't matter.
Well, the cool and frustrating thing about organic chemistry is that most organic chemicals are predominantly carbon and hydrogen, and then oxygen and nitrogen are very common in small quantities. And then you look at the number of possibilities for how you can arrange those, and there's so many different ways. But these are going to have very different properties. They're going to undergo different reactions. So identifying which one you have is not that difficult. Making one or the other, it's going to depend on what you're starting with. You don't make these things starting with elements. Organic compounds were originally things that could only be made by biological organisms, right? And biological organisms are very efficient in making organic compounds. It was at one time believed that you couldn't make them in the lab. Now we know that you can, and we do all the time. But it's more involved than the inorganic compounds. So good question. Here's a graph of boiling point versus molar mass, and we're comparing the hydrides of the group 6A and the group 4A. Wait a minute. Those are labeled wrong. Man, this publisher, good grief. This is group 6A. Of course, I didn't notice it yesterday. Those are group 4A. Good grief. Sorry. Those things bother me. Carbon, silicon, germanium, and tin, all in group 4, and they will form compounds with hydrogen where their formula is XH4. So if we look at their boiling points, we see that there's an increase in boiling point as the molar mass increases. These are nonpolar molecules, and so this increase is due to the larger dispersion force in a larger molecule. If we look at group 6A, they form compounds where you have 1 atom of the group 6A and 2 hydrogens. Those are going to be polar. So their boiling points are higher due to that, but we see the same trend with sulfur, selenium, and tellurium, again, with the increased dispersion force. And then there's water. We would predict, based on this trend, that water would have a boiling point closer to minus 100 degrees than plus 100 degrees. The reason that it's so high is because water has hydrogen bonding. None of these other things can do hydrogen bonding. So water molecules are very attracted to each other. They stick together. This is critical for life because without water, we wouldn't exist. And without hydrogen bonding, all the water on our planet would be in the gas state because the temperature, average temperature, is well above minus 100 degrees Celsius. So we should be able to answer questions predicting relative boiling points or melting points. And this is based on the presence of the different intermolecular forces. That was the term I was looking for. So what we need to do to answer a question like that is to identify what types of intermolecular forces are present in each of these. Yeah, this one has hydrogen bonding. This one does not. They're both polar molecules, so they're going to have dipole-dipole forces. They're both molecules, so they have dispersion forces. But hydrogen fluoride has hydrogen bonding because it's got that HF bond. Hydrogen bonding is much stronger, and stronger intermolecular force means higher boiling point. So this is the higher boiling point due to hydrogen bonding. There's a question in the homework where it asks you to select all of the types of intermolecular forces that are present in each of the molecules they give you. They all have dispersion forces. If it's polar, it's got dipole-dipole forces. If it's polar with phone home, fluorine, oxygen, or nitrogen bonded directly to hydrogen, then it also has hydrogen bonding. Questions? And then there's the ion dipole force. This is very strong, but it's only present in mixtures. You can't have an ion dipole force within a pure substance because it's an attraction between an ion and a dipole, and one substance doesn't have both of those. We talk about it because it's really important in the formation of aqueous solutions of ionic compounds. So here we've got sodium chloride. A chloride ion, in order to get it to separate from the sodium ion in the salt crystal, you have to make up for the loss of that attractive force of the ionic bond. And you can do that with the interaction between an ion and a dipole, so the ion dipole force. So it takes a bunch of water molecules coming around this chloride to make up for the attraction it had for sodium. So water can come around and lure the chloride away with it shows its positive side to the negative ion. And then two-faced water shows its negative side to the positive ion and lures the sodium away. And you end up with a solution. Any questions? Water's really cool stuff. This is a table summarizing the different types of intermolecular forces. You do not need to know the strengths in kilojoules per mole, but you should know the relative strengths. Dispersion, dipole, dipole, hydrogen, ion, dipole. What types of molecules they are in. It is important to note, here's this little asterisk, dispersion force overall is the weakest intermolecular force, but it can become pretty significant in large molecules. So it's all relative. When I ask you to predict things, the questions will limit the differences to one thing. Like the molar mass will be different, but everything else is similar. Or the molar masses will be the same and we'll have hydrogen bonding in one and a nonpolar in the other, something like that. Hydrogen bonding is really important in physiological processes, such as the replication of DNA. DNA consists of two strands, and they are held together by hydrogen bonding. The bases in the DNA strand are thymine and adenine, which can form 2 hydrogen bonds with each other, and cytosine and guanine, which can form 3 hydrogen bonds. So cytosine and guanine will stick together a lot like a magnetic key and lock. They'll just click in together and they form a really nice attraction. Cytosine will not match up well with adenine. And so cytosine and guanine always pair together. Thymine and adenine always pair together. So as your DNA replicates, the 2 strands are separated and a new strand is built using the old strand as a template. And so the new bases come in and correspond to, so if here's an A, you're going to get a T. And here's a T, you're going to get an A, and C, you'll get a G. And they always match up like that. Every once in a while there's a defect, and that can cause some significant problems, but most of the time not so much. Questions? This gets into biochemistry, which if you like chemistry and biology, you might think about going into biochemistry because you can look at chemical reactions that are happening in biological organisms. That's as far into biology as I like to get.